arrow. And then this 2405 is say unshoken ribbon. Okay, so far we have been discussing basically the this language which we are going to use for describing string field theory, and so we took a long time to just build up all this formalism, and but now I mean you will see that once we have this formalism, we can string theory has all the ingredients which are needed for this BB formalism, and we just have to put in appropriately. I should apologize because this will be very superficial, because now it will require me 3 more lectures to cover these things. But what I will do is I will at least based on what we have constructed so far, we will see how that is helpful for describing string theory. At least that part we will try to make it clear. So first I will discuss the bosonic case, then closed superstring, and then some open closed. Okay, so let me just start with some history. So the original formulation of this string theory, which was done was by Barton. So he formulated for bosonic closed string field theory, and then Ashok and Juibach worked out lots of properties and uncovered various things of this string field theory. And all the language which we will be using, I mean, this was developed by these Ashok and Juibach. So the closed superstring field theory was recently constructed. I mean, for a long time, the main problem was to include RR fields, and that was solved by Ashok in 2014-15. And about open string, so open superstring field theory was first constructed by Witten. So that was even before this closed string field theory by Juibach around 1985. But it was soon found that it contained divergences which correspond to propagation of closed strings. And there have been various attempts to reformulate open string field theory so that these divergences disappear. But one way to deal with these divergences was to explicitly add the closed string sector to open strings. So that leads to this combined open closed string field theory. And these kind of systems naturally arise if you have, for example, D-branes.
I mean, isn't that the same thing to do anyway? Because
right. Yes. So for the bosonic case, this combined open closed string field theory was constructed by Juibach in 1990.
It doesn't take too much time to ask for a couple of words on why open string field theory has divergences.
Yeah, I mean, so because once you have open string, you can form a closed string. Yeah, so basically, I mean, you will see that at tree level, there won't be any problem. But when you consider loops, you cannot avoid propagation of closed string. So once you have a open string, you can form closed string. So just having open string is not a consistent theory.
It's UV divergences of the open string. In the closed string, UV divergences are just absent. In the open string, they're not absent, but they can be interpreted as a closed string from the open common sense.
infrared in the closed string.
So if you account for all the fields in the open theory, then you will be able to do this, but if you cut it off, okay, more.
Yeah, if you cut it off, you'll get some uncontrolled. Yeah, divergence.
So this was constructed, this combined open closed string field theory in 90s by Juibach, and the supersymmetric version was recently constructed, including this RR. Okay, so let's begin with this closed bosonic string field theory. So what I will do is first I will
Sorry to see you, but so now we have a closed string field theory which closed plus open for the superstring.
Yes. So what I will do is I will first review some ingredients which we will need for writing down say string field theory action. So these are all very basic. So all of you know it. So the bosonic string theory is described by this worldsheet matter X mu and the ghost field B and C. And I mean these worldsheet fields can be expanded in a 2-dimensional plane. So you have a string propagating. So you have a cylinder. but by conformal transformation, you can map it to some 2D plane. And in that plane, you can do a mode expansion. So the mode expansion for a generic field, say phi, it takes this form. So here delta is the conformal dimension of the field, and it takes value 1 for del x mu, -1 for C field, and 2 for B. And the state space of the theory can be created by acting with creation operators on the vacuum. Now, so there is a family of, you can construct this family of SL2C CFT vacua, 1 comma P, which is obtained by acting with this operator e to the power I P dot X on 1, I mean this ground state. And so this family of vacua satisfy these properties. So for example, they are annihilated by these annihilation operator alpha mu n for all n greater than equal to 0. But for B and B bar, for n greater than equal to -1, and for C and C bar for n greater than equal to 2. Okay. And now since we have a ghost system, so ghosts also have, you can write down a conserved current under some U1 kind of transformation, and this conserved charge associated with this ghost current takes this form. And okay, we add this number 3 so that the ghost number of this SL2C vacua are 0. So these are some conserved quantum numbers. Now we have two 0 modes, B0 and C0, which appear in the theory. And due to this state space breaks into 4 different sectors, which are built on top of these 4 vacuum. So for example, you had 1 comma P, but since C1 does not annihilate, so only for n greater than equal to 2, this Cn annihilate this SL2C vacua. So you can act with this C1 bar, and this is perfectly fine vacuum. And then you can also act with C0 plus, C0 minus, and also C0 plus, C0 minus. So you have these 4 set of vacua on which you can build your state space. So here B0 plus and minus are defined in this way: B0 plus minus B0 bar, and C0 plus minus are C0 plus minus C0 bar by 2. And this vacuum down, the first one, has ghost number 2 because it has 2 C modes, and it is annihilated by all B and Cn. So it is annihilated by also B0 plus minus as well as all Bn and Cn with n greater than. Now the state space of this world sheet theory, it consists of states which are obtained by acting with all possible creation operator in these on these 4 vacua. So general state which are present in the spectrum take this form. So you act with arbitrary number of creation modes, which are alpha mu minus m, B minus m, and C minus m. And omega I could be like any of these vacua. So this state space H, which consists of all these states, is a graded vector space with each state having a definite world sheet ghost number. Okay. So let's denote by phi I the basis vector of this state space H. So, but we shall be interested in a subspace of this full state space. And what is this subspace? So we demand that this subspace satisfies these conditions. So this subspace should be annihilated by this operator L0 minus, which is L0 minus L0 bar. And it's also annihilated by B0 minus, which is B0 minus B0. And as we will see that these conditions are needed for a well-defined option.
The full vacuums that you constructed, all of those have same energy.
Same energy, right?
Or zero. Then zero energy.
Yeah, so you have to act with L0. So on this vacua, L0 will be like 0.
But you're not putting B0 plus on state.
No. So if you put the B0 plus also equal to, okay, so that, I mean, that is a special gauge. Okay. So what this condition mean is that we are working only with the states built upon these first 2 vacua we had. So this one down, and this up. So if you see, like, for example, the structure of these, for example, if you act with this B, let's say, okay, L0 annihilates everything. But because, okay, in the last two, there is a C0 minus. Okay. And so when you act with B0 minus, it will not annihilate because B0 minus and C0 minus have non-trivial commutation relation. So these two do not satisfy this level matching condition. The last two backward. Only the first two satisfy this level matching condition. So basically effectively means that we are working on the state space built on top of these two values. Now for each of these basis vectors phi I, which belong to this HC, which are this restricted Hilbert space, we introduce a target space filled psi I, and we shall assign a target space Ghosh number, which we will denote by this GH, in this manner. So the target space Ghosh number of this space-time field psi I, it is defined to be 2 minus Ghosh number of this corresponding worldsheet basis Ghosh number. And we construct now a generic element of this vector space HC, which would be given by some basis element multiplied with this coefficient field psi I, which are interpreted as target space. And using the state operator correspondence, we can also represent this operator psi as a state. So psi state you could write as psi 0 acting on the vacuum. So this is phi I 0 psi I, and then you can commute psi I across 0 because 0 is a Grassmann even, and you can write it in a state.
Is there a relation between worldsheet Ghosh number and target space Ghosh number?
I mean, so this is the relation
For any field?
for any.
So the vacuum, the one which you had C minus 1, I think that vacuum is Ghosh number 2.
Yes.
So you're basically in the frame in which your vertex operators are C times something. Physical states will have Ghosh number 0.
Right. So I mean, so phi I basically effectively represent our vertex operator. So that you can think of PC bar times B.
Yeah.
And for writing down the action of string field theory, we shall also need the concept of inner product in the state space of the worldsheet theory. So worldsheet theory is described by some CFT, and we need a notion of inner product in this conformal field theory. So in CFT, say in two-dimensional CFT, the BPJ conjugation is a natural notion of inner product. So for example, if this B, which is obtained by acting with operator B0 on the vacuum, denotes a state created by the operator B, then its BPZ dual is defined in this manner. So the bra B is defined by this bra vacuum acted on by this I of B, where I denotes the inversion operator. So for example, if you are working with some like modes, then the action of this BPJ conjugation is simply this. Now, using this BPJ conjugation, we can define this inner product in the state space HC. So A comma B denotes this inner product, BPZ inner product, and that is defined by insertion of an C0 minus in the between these states. Okay, so here A and B are the state belonging to this restricted Hilbert space HC, and this insertion of C0 minus is necessary because these states A and B are annihilated by B0 minus. If you don't have, like, say, this B0 minus, then what will happen is, suppose there is an identity here, then 1 is equal to commutator of this anti-commutator of B0 minus C0 minus. And then that B0 minus will kill either bra. So this will naively vanish.
It's flash the definition of HC again for me.
Yes. This one? Yeah. Okay. Now for writing down the action, we also need to introduce some geometric quantities. Okay. And let's to build the geometric quantity, let's recall some aspects of how we compute string amplitude. It's just review of what we also discussed in first lecture. So the G loop on shell string amplitude is computed by doing an integration over the moduli space of genus G Riemann surfaces. And the general structure of this G loop endpoint amplitude formally takes this form. So here this correlator V1 to Vn is computed on a genus G Riemann surface with n punctures. And Mi, this M curly MGM denotes the moduli space of genus G Riemann surface with n punctures. And Mi parameterize this moduli space. However, for string field theory, we are not going to work with this MGN. So instead of this usual moduli space MGN, we shall work with an extended moduli space, which we shall denote by PGN. And how it is different from MGN? It contains information about the local coordinates around the punctures. So you have some Riemann surfaces on which you have inserted some operator, some vertex operator. Usually, when we consider when we try to compute the on-shell amplitude, we don't care about what is the coordinate system around the those vertex operators. However, when we are going to construct this string field theory, those coordinate system play a role. So you can think of this coordinate system as some kind of fiber over your usual moduli space.
Another way of saying it is that it will depend on the Y factor.
All right.
That normally in string theory, well-sheet amplitudes are independent of the Y factor. Now it depends.
Yes. Okay, I think I should apologize because this, okay, and forget this N, there is only one index in bosonic case. N is for okay, this diagram I took from superstring case. So there, okay.
But is it exactly the same that you will keep track of not just the complex structure locations of all points, but also the value of the Y factor? Is that exactly the same? PGN is Y factor plus. Okay.
So we have this information. So each point in the x-axis represents a Riemann surface. Okay. So these denote the moduli spaces. And on top of this, the vertical direction contains information about all these coordinate systems. Okay, the meaning of this curve will be clear shortly. So
say again, but the title will be that whatever worldsheet tube diagram we have, we say that
worldsheet loop diagram.
Tube kind of
Tube diagram.
The worldsheet diagram.
Right.
We say that this is like a vertex, and then it's propagate.
Mhm.
We try to make it back into a Feynman line.
Right.
That is what probably a thing that there are elementary vertices.
Yes.
But then how do we do from there to saying that there is a Y factor present now? There's a shade factor of it. We didn't follow the earlier discussion.
Yeah, so basically, I mean, so Y factor basically means if okay, you make a coordinate transformation. Okay, so there will be so suppose let's say you have some Wi coordinate system around the punctures. You make some Wi to f of Wi. Then in the vertex operator, this f of W will be present now. And yeah, okay.
Let me say it my language. Right? You know, in string theory, the answer to the worldsheet, the while thing is fake. Okay, and you see that it's fake because when you go from Nabu-Goto to Polyakov, it's like a one-to-many mapping. One Nabu-Goto configuration maps to Polyakov configuration with all Y factors being the same. Just really engaged. Redundancy, very huge. And but to maintain that fakeness, you need that the vertex operators that you insert are 1. Because when you have 1, then D2 is a square root G. The Y factor dependence of square root G cancels the Y factor dependence of the insertion. Okay, so with 1 vertex operator insertions, the Y factor really does not enter any. Okay, but now we want to go off. This 1 is the equation. If you want to go off shell, you're going away from equation. So will no longer be 1. So the vertex operators you will insert will no longer be while in there. So it will depend on the Y. I mean, we'll no longer have wait. Yeah. And then people who are mathematically minded like to say in terms of these problems. I think.
Okay. So and now, so
And just to ask you, but ultimately, at the end of the day, different choices of coordinate systems will be equivalent because there'll be field redefinitions.
on shell.
I mean, all the on-shell content will be
Yes.
field.
Yeah. So, in fact, I mean, so if you consider these Riemann surfaces and then try to like, okay, because I'm not going in detail, but it's like there's a whole structure behind like this structure. I mean, this geometrical concepts. So what you do is you view these Riemann surfaces as obtained by gluing disks with say, and suppose you are considering genus G surface with n functions, then you consider n disks and some 2g minus 2 plus n number of sphere with 3 holes. So any genus G surface can be written as a gluing of like these two objects. And now, so you glue them along some circle, okay? And by considering the transition function across these gluing circles, so all the information about moduli spaces is present in those transition functions. So that way you can build up all the like this machinery. But okay, I'm not going to describe that because that will take me separate one lecture. But that's the like this information is there in all these fiber diagram. Yes.
Is there a map? Maybe you say this later, but is there a map of what this redundancy maps to on the field theory is?
Which field theory side?
Field theory.
Yeah. So I mean, so all this redundancy is present there.
So what does this Y factor redundancy, like Y factor dependence map to on the field theory side, like something in those options?
So maybe I mean I'm not understanding the question. So
You say make different choices, you get different string field theories. What's the
not is different. Okay, so you what you can show is if you compute the on-shell amplitude, then these like choices will not make a difference. Okay, but like these, so it's like working with off-shell theory.
Yeah.
If you want to like write down a Feynman diagram kind of description, then these different choices will play a role. We will consider like these Feynman diagrams, and maybe there it will be clear.
And like what do we so if you make a different choice, would it map to like field specific kind of each definition?
Yes. I mean, okay, you have to, yes.
You tell us later.
Yeah, probably I will not go into the detail, but maybe at least I will show how you generate this Feynman diagram. Maybe there it will be at least something will be clear. So okay, so in this whole this PGN, you have okay. So this point we also discussed earlier that so there are regions in moduli spaces which involve the degenerations, and then there are regions which are free from degeneration.
When you talk about these, just a complex structure moduli space, you can also parameterize that by just disks. And then these transition functions.
Right.
So now what additional element comes in here when you're going beyond this complex structure?
No, I think everything, I mean, there. That transition function has everything.
Just out of curiosity, sorry, you must go on, but do you glue the coordinate systems you're using under the analog of Fenchel, Nielsen coordinates? That is,
Yes, I mean, that is one choice.
Okay.
That is
Something like that. But
Yeah.
then if you do around geodesics, that also carries.
Right. So that is one.
Sorry, just to go back. In the normal situation, when you're on shell, if you make like a coordinate ring definition plus holomorphic, it does nothing.
Yes. So those will be like so you have to mod out by so fiber direction does not contain information.
But here it will.
No. So holomorphic ones like you follow. So there are regions where you have like degeneration. So we denote. Okay, see this solid line represent these surfaces which you can obtain by gluing. Plumbing fixture, and then there are these elementary like regions which are free from these degenerations. So and these degenerations in general can be of two types: separating type and non-separating type. So if you have a degeneration which is obtained by gluing like two different surfaces, say lower genus and lower point surfaces, then it is called separating type. So if you cut along the propagator, it breaks into two parts. So that is separating type. And non-separating type is one where you have a single Riemann surface, and then you like glue you join two punctures by a tube. So if you cut along this tube, it does not break into two parts. So it's like one pi, one pi. And the elementary region, VGN, exclude all type of degeneration, separating as well as non-separating. So for constructing this field theory of string, we will need an analog of these interaction vortices.
So you find some elementary square problems basically. What was this elementary?
Oh, this VGN, which exclude all the degenerations.
And what does it mean? We exclude things when it gets narrow enough.
Yes.
So there's some particular size.
Yes. So basically, the point is, yes. So you can choose some value of, say, suppose you parameterize this gluing by some kind of Schwinger way, and then for some value of S0, you can declare that, okay, beyond this, I will not include in the.
Say putting the cutoff.
It's like a cutoff.
There's some constraint on combination of the while plus complex terms.
Right.
So it's
Yes.
And keeping track of this is not cutoff will be the same as keeping track of the white factor.
Not. So that information will be there, of course. So we need to define the analog of these interaction vortices. Which will enter into the string field theory. So we define this off-shell string vortex in this way. So this curly bracket with say n insertions is defined in the following way. So here GS is the our string coupling with this power, and we sum over all this infinite genus. And then we have these regions VGN, which are elementary regions, and then we have some p-form field omega p, and they depend on these insertion a1 to an. So this omega is a correlation function involving n external string states on a genus G Riemann surface, and it includes information about the local coordinates around the pointer, which are these off-shell data. And this VGN are so I defined this VGN.
Which I'm what A's are again going to?
A are some insertions, so they will be string field. They will turn out to be. You can choose them. They are off-shell vertex.
And what is preform field?
Yeah. So yes. So that I think. Yeah. I'm defining this. Preform.
Just to understand, on the right hand side, you will simply do the worldsheet integral.
Worldsheet integral, but now with the off-shell data.
With the offshore data, so you will have to keep track of the coordinate
Yes.
systems and so on. But you will just do it in this restricted.
In this TGM. Yes. Yes.
And you're integrating only in this elementary.
Elements.
You're not.
Yes. Yeah. Not along this. So this off-shell amplitude that involves integrating a p-form field, which was this omega p, because we want to integrate over PGN. So we have to define a p-form field, and that omega is that p-form field. And this needs to, we need to appropriately define it so that it contains information about the off-shell data. So this V1 to VP, suppose they denote some tangent vectors in your PGN. Then since it is a p-form, you can define it by giving its contraction with all the tangent vector. That's how you define p-form field. So the contraction with some arbitrary, say, p tangent vectors of this omega p is defined in this. So this is the correlator, where this b is it's constructed in terms of this Beltrami differential. This b and b bar are your b coach fields. This ai are the insertions. They depend on the in which coordinate system you are inserting. And this is computed on this Gina G Riemann.
I thought PGN was your underlying Riemann surface with the vector bundle kind of structure involving the coordinate system, right? So now the tangent vectors on that, how are they related to the space time? A1 to AN is space time
A are your vertex operators, the worksheet so there are some operators.
Tangent vectors are given.
This V, capital V.
Right.
This capital.
This B of V, right? This thing with that mu z z. Small changes in what?
Yes.
That small changes, I agree with you. But okay, then, so what's the tangent? So V1 to VP are tangent vectors
in
on
PGN,
right?
in
So
yes,
in this whatever vector bundle you're getting. Okay, sorry, and just go back once more to that slide.
Yeah.
So that's what we went to, and A1 to AN presumably is or omega P is a P form.
P form
in this thing.
Yes.
So what you do is, okay.
So
Tangent vectors are basically the mu z z. Small changes.
yes.
Is the P fixed? If you have fixed the number of insertions?
Yes. Yes. So P, I mean, so in general, this P will be the dimension of the moduli space. So for botanic string theory, it will be some 6G minus 6 plus 2. So we have to construct this 6G minus 6 plus 2 and dimensional P, I mean form. So now some fact. So in PGN, if we move around a closed curve, then the quantities will differ by a phase. Okay. So for example, if you make a transformation of
Let's suppose we were on the sphere.
yes,
Then in normal on shell, we put C, 3 of the vertex operators are fixed,
right,
and the remaining guys are integrated over. Where is that element?
yeah. So here we will represent everything by this vertex operator. So so because of this B insertion, suppose you have so we only use the unintegrated vertex operator here.
Yeah.
So the integrated one appear after you contract with this B. So because there is a B, it will kill C present in this AI. Suppose one is not integrated. And then
so even though the number of vertex operator insertions is not the same as the number of beats.
no.
There would on the sphere there would be 3 less beats than vertex operator. Now
exactly. So suppose you make a local this coordinate change around the ith puncture. So suppose the coordinate system around this ith puncture is Wi, and you make this rotation e to the power I alpha Wi. Then the rotation operator is L0 minus L0 bar. So this state will pick up this factor e to the power I alpha L0 minus L0 bar acting on AI. And if you want your state to remain invariant under this phase rotation, then we must impose this L0 minus L0 bar equal to 0. And this was one reason why we had to impose this condition. And another, if you do a similar analysis for the differential form omega p, you demand that this omega p remains remains unchanged as you go around the closed curve. Then it will be possible only if you impose this condition, because the phase pickup will be proportional to B0 minus B0. Because it has all these B fields. So one can do analysis and you can show that.
BRST current commutator with B0 minus B0 bar is L0 minus L0.
Right.
Does that play a role in this?
Yes. The derivation.
Does L0, does the arithmetic condition have a translate naturally into the field theory?
It's like field theory. So field theory you mean on the on-shell because our whole construction is built upon this condition.
Okay,
so if we are not relaxing this condition.
I mean L0 equals 1. Oh, I see. So when you say off-shell, you still have L0 minus L0.
Yes. Okay. So this was just to show why we had to impose this condition, because we are going to work off-shell, and in PGN these conditions are necessary to have a consistent interaction.
Would there be additional conditions, because you also have to keep track of the local coordinate systems as you go around and you see this
loop
as you go around.
Okay.
The cycles in this vector.
Yeah. So they are giving you this.
This is enough.
This is enough. So we had discussed.
This would not be enough for in terms of modular invariance. this would be enough for the P modular invariance, but not the S modular.
Yes.
So just going back to the question, I don't know what the question is, but it feels like you're imposing part of the requirement for modular invariance. The part that you can do continuous, right? But not the part that you have to do discrete.
You are saying due to modular invariance, there will be like some additional constant.
Tau goes to minus 1 by tau requires what invariance under what invariance. Okay, that you're giving up. But you're keeping the invariance under tau goes to tau plus 1. That's effectively when you say L0 minus L0 bar is 0. So that one of the things that ensures is invariance under tau goes to tau plus 1, right? Because the speed is 0. So this ensures that as you go around, I feel that there's a continuous versus discrete here. That you're not going to get the same answer if you just view the torus differently. Right? Because it's sort of off shell and only on shell will you get that same answer.
Right.
But you want for continuous things you want to get, like, is that roughly right?
Yeah, maybe I need to think more.
I need to ask the
but,
question more precisely.
So the option is that you're imposing a selective condition on the dimension, right? Are you giving up on quantities? Is he still working with the modular invariance safety?
No,
So modular invariance will emerge, but
what I mean is that modular invariance the CFT is there, but now this answer for string theory depends also on the y. Okay, and in order to get tau goes to 1 by tau, you need to be able to rescale them the terms. So anything that depends on the y factor will not have that tau goes to 1 by tau.
When I do the tau goes to 1 by tau, I get a different y factor and hence a different answer. And when I rescale,
right? Because what you get is that tau goes to 1 by tau is the same. You get similar tau, right? Not equal tau. You have to do some rescaling. But if tau goes to tau plus 1, it's just lying on this. There's no rescaling. So it felt to me like you're keeping those things that don't require y factor rescaling because you don't have the y factor. But you're giving up the variances that require y factors.
okay, I mean, yeah,
Roughly.
think okay. Yeah, probably I need to think more because this moduli space information is already at the base. So we are doing something on the top. So
On the top, yeah. But you were putting this condition that you move around in that top in some ways and it doesn't change.
It doesn't.
But in other ways it will change. I think that I was my 1 by tau.
So because when you project onto the base, you will get the usual
We will get the usual thing on shell, right? The question is about whether it depends on the fiber.
Okay.
And some things will not, but some things will. That's what you're losing by going off. Right?
Okay, so we had.
So sorry, but it just in the previous slide, that state AI, just so I understand. This is a state in space time.
This is a state in your CFT. I mean, CFT.
Worksheet CFT with coordinate system.
Right.
state corresponding to the operator.
Yes. Yeah. So I mean, this will be a state of this kind. I mean, we constructed here.
Just some of
This.
data acting.
So this phi I are your vertex operators, psi I are some space-time fields, and so this AI will be like.
Sorry, what are space-time? Sorry, psi I are vertex operators?
No, phi I.
Psi I the
Phi I are the vertex operator, and psi I are some space-time target space.
But so you can encode that all in the vertex operator. I mean, even this
no,
target
so-
space dependencies.
So here I mean so phi I denotes here CC bar times V. It's, and the psi I will be your some space-time field like say A mu and so on. There's a coefficient. basically. Yeah.
K or something
Yeah, yeah.
like that.
Well, ABO?
K, like
Yeah.
the moment.
E to the pi kx.
No, not e to the power.
Vertex operator. So just how much of that?
Yeah, how much of that? Like, so dependent on K or whatever.
Okay, so we had this elementary region VGN, and what you could do is you could add to VGN this non-separating type degeneration, and you would get a 1 PI region RGN. Okay, And so 1pi interaction vertices are defined by the same expression as before, but now the integration is over this arm. Okay, and this will be later useful if you want to construct an analog of 1pi effective, for instance.
The non-separating type regions were the elementary regions.
No, they are not elementary regions. So they are degeneration. They have degeneration.
Okay.
So you, if you add this elementary region to this non-separating type, you get this RGN. If you want to have an analog of 1pi, then we will need to integrate over this RGN.
So adding this degeneracy will not give me a divergence.
Sorry.
So the degeneracy will not give.
So now in this framework, it will not give that.
These elementary regions were the regions with cutoff.
Yes, I mean yes. So you are identifying some region which exclude this degenerated Riemann surface.
And then you are adding just the non-separating type region.
Yes. It's like, I mean, what you do in also field theory, right? I mean, so you when you consider 1pi, then you exclude all those diagrams which can be divided into two if by a single cut. But you include everything else.
And what is the analog of separating type here?
In QFT, it's so I mean separating type would be like a diagram which if you cut,
Okay.
then it gets separated into two parts. So to write down the action, we need to introduce some more quantities. So we define what is called this multilinear string product. Okay, denoted by this bracket A1 to A. So this is defined in the following way. So
yes, to ask you, now that you are allowing for those degenerations, these worldsheet integrals will be well defined.
Yes. So I mean, in this 1pi, so we are not considering the this separating type, but not separating.
But they'll be well.
They will be. So so this multilinear string product is defined in the following way. So you have this square bracket and its inner product, BPZ inner product with some arbitrary state A0. Sorry, I think it starts from A0. There is a typo. So it's A0 to AN. So it's basically the inner product between arbitrary state A0 and this bracket A1 to AN. And just as vertices, we can also express this multilinear string product as sum over all this genus.
And define the multilinear string product. The A0 was also on the top line.
Here.
No, also at the top line.
No, not here.
So you've chosen some special A0.
No. I mean, it's some arbitrary state in CFT.
So that multilinear string product doesn't have information about the A0 then.
Yeah. I mean, so it's defined in the way that its inner product with any arbitrary state gives you this vertex.
I see. Yes, it's an OP.
Right. So
The left hand side is some worldsheet integral.
it's a BPZ inner product.
Yeah.
Well, the left hand side is like a vertex of it. Right? What? Yeah, some state.
You mean A0.
A0.
Bracket is a BPZ.
But then you have to do some.
So it's basically OP, right?
Yeah.
A1,
I mean, A1
it's replaced by one now. One out. Isn't that right?
Yeah.
Well, just because you want to keep track of y factor will do everything.
You're saying is that left hand side integrated? I think.
So this integration, of course, in the right hand side, there is an integration in the definition of this curly bracket, the way we had defined earlier. So that had all the information about coordinates and so on.
So Sandeep's question is important because I was thinking of this as fixed positions.
Oh no,
fixed position
no,
will
it's
be like
not a fixed position.
Okay.
I mean, OP in the sense like if you consider like say just 2 point or something, then okay, it's like a trivial. Then there is no integral.
In general, but if that's
But in general, yes. In general, it won't be like just be reproduced by you. But what you could do is you could so suppose there are n insertions on like a surface, and then you separate out one, and then the rest you call like some state in CFT. Some state say sigma. And that the effect of like inserting that like state sigma will be like reproduced by this square bracket.
But when you say some state in CFT, if you're before doing the integral, That's sort of clear, right? Because that's just you. But how do you know that there is something after doing the integral? This is not a familiar note.
Something after the integration.
You're saying that maybe I'm not understanding, right? But you're saying, what I'm understanding is that you have an n+1 point, integrated vertex operators. One of the operators is A0, and the remaining n are A1 to n. And you're saying that that having the effect of having this A1 to n and integrated is the same as can be reproduced by the effect of just one operator integrated.
Yes. So this this operator.
No, but how do we know that it's such a? It's not.
Oh, I mean, it is. I mean, it's just a CFT property. I mean, this is
CFT property is without integration.
Without integration.
So this statement is with or without integration on the worksheet.
Left hand side.
Left hand side, right hand side. Both.
So left hand side is it's just an inner product between two states.
So those are fixed locations on the.
So fixed location meaning so there will be of course information about all the coordinates in this.
But fixed, no integration of position.
No integration.
The right hand side has no integration.
No, right hand side is defined by the same expression we had here.
But how can the right hand side contain information
No, so
locations and right hand side not contain?
Yeah, so what you are basically doing is
No, the right hand side doesn't.
no. So right hand side is defined by like this expression. So in this way, there is an integration of this modelized space, PGN.
And does that know whether the locations of the does the right hand side know whether the locations of A1 to AN?
This has been integrated out.
Integrated out. Okay.
Yes.
So right hand side has no information about where they are.
Yes.
So does left hand side have information?
No, it should not have because
What
it's
is
just.
left hand side?
So this is just the inner product between these two states.
State.
Okay.
What is a state? A state is, I understand state in CFT.
Yeah.
But then you're doing CFT and integrating over moduli space, right? Over locations. What do you mean there by state?
So this one. So this is.
I don't understand any of those.
Okay. So this you like understand, right? I mean this we had defined.
This is just vertex operators integrate.
So they're integrated.
Yeah, it's like
It's some function. Yes.
Yeah.
And this left hand side is so you are taking this VPZ inner product by considering A0 with some you are defining some notion. I mean what is called this surface states. So this square bracket denotes some surface state whose I mean if you take inner product with A0 it will reproduce like this one.
But state what is this stated as so sorry. Is it stated in CFT in space?
Yes. Maybe okay. I'm not maybe.
What I understand in CFT Hilbert space is that there is a Hilbert space which is basically the Hilbert space of operators, local groups. The inner product is you put one operator at 0, the other operator at infinity, compute the function. Right? These are not integrated components. Now, if you put at some particular locations, you can do an OP, replace it by one operator at 0, and that notion I understand. The integral is confusing. Maybe you're saying the integral doesn't matter.
Yeah, I mean here, I don't see because.
Okay.
So the way I mean, it is. Let me think.
This square bracket is the OP result of that.
So here we are not really taking OP in general. I mean, so it's a.
You're saying this is an abstract.
Yeah.
Sorry. I mean, is that a definition or is it a?
It's a definition.
It's a definition. Okay.
It's a definition.
So the right hand side is clear.
It's clear. Yes. Left hand side is defined by this.
So what's not clear to me? I mean, how is the left hand side a definition of the multilinear string product?
Yeah, because so this is the BPZ inner product. So you define this state, some abstract state you define in the CFT, and you take inner product with some A0, and the result of that inner product BPZ inner product should give you like this.
Definition is not on shelf.
No.
But what I don't understand is that left hand side you're taking inner product in what Hilbert space? Because
CFT,
CFT
standard CFT.
But CFT Hilbert space doesn't involve all this integral. Okay, so whatever. So CFT Hilbert space. So you're using some vertex operator.
Yes.
Okay, good. So left hand side is CFT Hilbert space, right hand side is a number. Fine, now I understand. There's just some definition.
Yeah, yeah. It's a, I mean, inner product between two states, which give you number, and the right hand side is a number.
But, sorry, but what? How can the left hand side depend on A0 and the right hand side not?
Oh, it is there. I mean,
Oh, it's there.
this is what I said. I mean, it starts from A0.
Okay.
Yeah.
Is this a fixed reference?
It has some arbitrary state in your.
So if I understand, just to understand, on the left hand side, I would just take in the CFT, the operator A1 to N at whatever locations they are at. And A0 and take the inner product with A0 in the usual BBC way. And then at least I would get something which depends on the locations of 1 to AN.
No, so right hand side does not depend on the because it has been integrated.
So now I'm still trying to think.
I think what I understand. What I understand is that he's defining an operator, just an operator without a location. That operator will be inserted. Let's imagine that the A0 is inserted at infinity. Operator will be inserted at 0.
Zero.
Okay. Now the question is, what operator do you have to insert at 0? So that the the 2-point function of that operator with A0 is A0 without.
Yeah.
That's the difference.
Yes,
That's
that's the difference.
And let's say that A0, we choose like an orthogonal basis of operators, then that operator, whatever it is, that A1 to N, will be something times A0. But you want it to be true for every A0. No, so something like I see. But you want it to vary over all. So okay, fine, got it. So now the question is that it's clear that there exists such a thing.
No, it's not. Now that you explained it, it's not so clear.
Yeah, so no, so this state does exist. I mean, okay, you can construct it in instant field theory. So it's some surface state.
I see. I'll tell you what I understand. So suppose you take A1 to AN and then put instead of A0 I'll call it B.
Okay.
You take B and you vary over all. Now the left hand side gives you the inner product with B. Let's say B is an orthogonal set of states.
I see.
So it's just a coefficient.
Okay. You define it like.
Yeah. Okay. And since it's linear, then the right hand side is linear, then it doesn't really matter. Yeah. Okay, got it.
So this square bracket satisfies some useful identity, and one identity is this. If you act with this BRST operator, then the action is given by these terms. So basically,
is there something physical? Sorry, the square bracket sounds like very interesting. I've never seen it before. Is there some physical way of saying?
So it's suppose you are considering some endpoint function, and then you have some one external state coming out, then whatever is the rest. So basically, I mean, what state you have to add to the say n-1 point vortex so that you get the endpoint this. So basically, it's like cutting off say one.
It's like
one
the
external.
Is it like the out state? Suppose I think of
out state.
Suppose I think of the. Very roughly, I'm thinking of it as scattering A1 to AN to B.
Okay. Yes.
So then A1 to AN are sorry in states.
Yes.
And then the out state.
Yes. Is like
the coefficient of all these the out state is.
If you have a degeneration surface with A1 to AN on the other side, you want to see what's on. If
sorry?
you have a degeneration surface.
So I mean, so here we are not including the degeneration surface in this definition.
Yeah, I just meant like when there is one such, let's say you have.
We will not introduce, I mean, this for the degeneration.
Is there a property where you can take A1 to the bra?
A1 to the bra. Yes, I mean you can because I mean here so it depends on how you mix these. So suppose you suppose you have A0 here and then A1. You can suppose they are all even. So you could just swap them. And then accordingly, I mean, it will be defined. So there is various identities, properties of these.
Is it possible to define such product in standard QFT?
In standard QFT. So I mean, this requires this VPZ inner product. So
my question
there
is,
you have.
can I replace n-1 vertex with 1 vertex?
Yeah. So there, I mean, I'm not sure whether it will be useful. I mean, you can try to define, but I don't think. So there, we don't have this notion of VPZ inner product. There we have Hermitian conjugate. So there probably it won't be very useful. And it probably won't make sense. Yes.
So also the way the state is defined, it feels like it will be fixed only up to null states.
Which is state?
Square bracket.
Uh-huh.
So
Because it is 0. Yeah.
So the component of that state along the null state will not matter.
Right. Yeah. So we have this like identity, and it's a very useful identity. And so let me just explain various terms of this. So what we are doing is, so you act with this operator Q. So the first term just represents how Q acts on like various terms of various insertions of this square bracket.
Q is BRST?
Yeah, Q is BRST operator. Then second term, what we have done is you have this set A1 to An that you partition into two like subsets. One contains L elements and the other contains K elements. So AI1 to AIL and J1 to JK. And then you have this kind of like partitions with these two square brackets. And then the third term, so here also you have this A, and then we have these basis states phi S, phi R, and then we also define these conjugate basis states phi SC, which are defined by this property. So what is the physical interpretation of this identity? So the physical interpretation is, so basically what it does is, suppose you act with Q. So you can convert this identity in terms of like this curly bracket. When Q acts in like your state, its action in your this PGN will be represented by some kind of total derivative. And that total derivative, basically, if you do an integration by part, it will give you the boundary of your elementary regions. So the left hand side is like that part. What is right hand side? Right hand side now, so left hand side, okay, denotes you this boundary of this this moduli, I mean boundary of these elementary regions. And the right hand side, what it says is that that boundary can be reproduced by gluing lower genus Riemann surfaces. So how it is gluing? So this the second term. So that
why is the left side a boundary?
So the action of this Q in the PGN will be represented by some total derivative. Because
PGN meaning sorry, PGN.
PGN.
In derivable model.
This region was the full 1 pi or the 1 pi with
No, 1 pi.
For the full 1 pi.
Sorry, I mean,
with those
sorry, I think I said something wrong. So elementary region does not include the this degeneration.
So then it will have boundaries.
Yes,
in those
yes,
places.
yes, yeah.
So if the BRST charge on an optional amplitude is some.
Sorry.
So the BRST current on optional amplitude is some non-conserved current.
Non-conserved current.
Is it a total derivative even when the amplitude is option?
No, so that's why I mean we are saying so there are these extra pieces.
Those are the
Yeah. Okay. So how do you get this boundary? Is basically you glue lower genus Riemann surface. So this second term basically represents like that part. So you consider L insertions, so this Riemann surface with L insertions and a Riemann surface with K insertions. And then you vary this L and K, and then you consider all sorts of gluing with these partitions. So that is one part. And this second part that encodes information about this non-separating type denominations. So basically, this identity says that boundary of those elementary regions are given by all sorts of gluing, all sorts of like creating surfaces with plumbing textures.
And why just two partitions?
Sorry.
Just two partitions of.
Yeah, so I mean, so we had only two kinds of degenerations. One was separating type, other was non-separating type. So separating type is like this one, and non-separating type is like third.
So I'm just asking you, as a matter of algebra.
Yeah.
Q acting on a vertex operator gives you total derivative in moduli space.
Mhm.
Certainly, when the operator is on shell.
Mhm.
Is that statement just algebra?
So, I mean, that you can see here. I mean, there are extra these terms.
These extra terms, sorry. So, okay, so but did you say that everything is associated somehow with a boundary or not?
This one was associated with the boundary.
And those other two are not.
This is not. I mean, this is. I think okay. I could have just taken to the left hand side.
Fine.
What is the interpretation of that first term on the RHS?
This one. Yeah. So this will this you will also get on shell. Like this, just the action of Q on this AI. Suppose you have like Q, you and so you represent it by derivative, but then you can do integration by part. Then it will act on like each this.
What was the third part? Can you explain?
Third part is this one. Yeah, so third part is like this one. So third part. So degenerations have two kinds. One is this separating type, and the other is non-separating.
So were it to have been on shell that if you could go back to you.
Yeah.
Were it to have been on shell, that first term on the right hand side would have been absent.
Yes.
Got
Because I mean this Q
it.
AI
Would have been towards the boundary.
Because they would both be zero.
Which one? Yeah, I mean it will be trivialized. I mean.
No, but then you're integrating some part of boundary. So there'll be boundary terms, right? Even not.
Just to understand, I mean, so I know all this without keeping track of the Y factor, but is it true even keeping track of the Y factor that if you have some genus G Riemann surface and you have some notion of the non-degenerate surfaces,
Yes.
that you can build them up by gluing the lower guys, each
Yes.
of which also meet the conditions.
Right. Yes. Yes. Yes.
This is all understood.
Right.
Sorry to take this back up again, but the ambiguity we were discussing earlier in the definition of the square brackets. So
Which ambiguity?
she was comparing with the right hand side, not depending on the position
Right.
of insertion. So those insertions so those ambiguities now go into your cutoff for definition.
But there was no ambiguity, right? I mean, it was.
And you just misunderstood.
Yeah.
You're putting an operator at zero. The ambiguity is what Okra was for. That you define the perfect state of the product is perfect.
So this main identity, so that is the geometric version of this L infinity structure here.
So the inner product is not positive. It is not because it has B and C.
Yeah. So this main identity is the geometric like analog of this L infinity gauge structure. So for example, at level 1, this main identity simply gives Q square equal to 0, which is just the it shows that Q square is nilpotent. At level n equal to 2 and 3, okay. At level n equal to 2, which means basically you are considering 3 point, and for 3 point there is no degenerations. So that's why you don't have like any the second and third contribution.
Sorry, where is square root
Here? Yeah, this just this.
Come out with that.
Oh, so basically, it's actually so the definition of this bracket at genus 0 is just Q times A. Because for 2 point you just defined this bracket by this inner product,
C,
which has sorry.
is it because the B in the middle?
B in the middle.
Okay, so it's B.
Yeah, C0, C0. But for 2 point, it is. I mean, for 2 point, it represents sort of kinetic term that will. I mean, we will see that it has Q in it. So that's why this square bracket with single insertion at 3 level is defined to be Q times A, and that's it just inputs like this information for n equal to 2 and 3. So for n equal to 2, which means we are considering 3 point sphere with 3 punctures, and there is no like degenerations. So there is no term of coming from second and third. But for n equal to like 4, where you have a sphere with 4 punctures, then this identity gives you this. So these 3 terms now represent various degeneration limits. So when unfixed puncture goes close to say z equal, I mean 3 these fixed punctures. So
Very sorry, but how did Q A0 from Q square? What was that?
this so this square bracket is defined to be q times a for the n equal to
How did it become Q square?
oh, because there is q already present.
Oh, square bracket.
Square bracket.
Oh, I see.
Yes. So yeah. So this I already said. So geometrically, the main identity basically means that the boundary of this string vertex region is reproduced by sieve lower vertices. Yes. So now we are ready with all this like ingredient. We can write down this quantum master action for the string field. So it takes this form. So let me explain each term. So the first term is the kinetic term. So this is the BPZ inner product between psi and then this Q psi. And these are interaction terms. So you have this 1 by n factorial to avoid overcounting, and then you have this psi to the power n. So this psi to the power n means there are these n insertions of this psi field. So all these a1 to an are psis. And this is the elementary vortex region which we had like defined earlier. So suppose now you want to find the equation of motion, you just vary. The variation gives you like this. So there will be two terms coming from the first, and both of them add to cancel this factor of half, and the second term gives you this. So the equation of motion would be given by expression like this. So q psi plus, okay, this typo.
So that psi to the n is just integration of the vertex operators over some part of one.
Which one?
Psi to the n.
Psi, yeah, psi, this bracket.
Yes.
Yeah. So here we are considering this elementary region. So integrated over the elementary region.
How we come with this action?
How we so this was, I mean, this is what they like constructed. I mean, so I mean, okay, I'm not going into the like how historically like people came up with this, but once you have this, I mean, okay, it satisfies all the properties of you expect from the form.
First term is going to be as the kinetic term and the rest are the higher.
These are interaction terms. So I mean here even say for n equal to 1, I mean if you have this hard genus contributions, so they will contribute.
And yeah, so you know, but when I go to some string field theory talks, sometimes they say, oh, you know, in string field theory, we have some decomposition of the moduli space and the vertices include little stubs and etc. etc. And all those little stubs are obtained in your psi to the n from your definition of what the restriction.
So stubs means stub basically means you are I mean how you restrict your elementary
region.
Yes.
So all that goes.
So that goes into the. So the main problem is to how you construct like these. I mean, so there are like various proposals. So one is this this minimal area like Barton constructed this minimal area like decomposition, and then there are recently there was this hyperbolic these vertices. So you can consider the using this hyperbolic geometry. You can identify some elementary regions. But I mean, so calculationally, if you have some computer, then okay, you can like put it in computer and you can try to compute. But analytically, I mean, it's still like very challenging to like compute these interaction.
The elementary regions are the non-geometric.
Yes. Okay, so for BV, one can now identify the fields and anti-fields, and they are identified in the following way. So this string field is like a general element of like this.
Just so you've broken. Is it right that you've broken up your moduli space into two parts? One of which you're associating with propagator, and the other of which you're associating. And the fact that this part that you associate with propagator, you've taken one part and made it this.
Oh,
just these long tubes, right? That gives you exactly Q psi. So there's a very specific decomposition that does this.
Yes. I mean, so specific. Yeah, I mean, so the propagator we identify. So I will write down the expression of propagator shortly, and then how you like. So basically, there is a lot of ambiguity in how you like identify your elementary region. This is what I
at least on shell. Suppose yeah, I'm trying to understand this ambiguity. Um, if because one part is somehow the propagator, right? Is that correct? That
Yeah.
One part is propagation and the other part is interaction.
Mhm.
Now, if you know what your propagator is, then the interaction should be fixed up to feed it.
Yes, but yeah. So, but the point is, I mean, which region you include in the this elementary vortex? So that region is like not fixed.
But suppose you change that region, then you should also change your propagator, right?
I mean, so it's so yes. I mean, in fact, okay. When I discuss the expression of this propagator, it will be clear. So there is an ambiguity. That ambiguity is associated with the systems, which I was saying.
So even the propagator is not always just 1 by cubes.
So
Because
okay,
they're
it's not just
very
1 by q.
particular.
No, it's not 1 by q. I mean, okay, so we have to invert like this operator, which will involve something like 1 by L0.
Got it. No, but you've got a very particular propagator. It doesn't seem ambiguous.
So okay, so what will happen is so there will be like some B0, Q acting on
All that,
Yeah.
good. You get 1 by L0.
yes.
But I'm saying that if you change your interaction region, you might have thought you have to change that left hand side. That
No,
second.
no. Okay, so probably it will be clear when I describe the vortex. I mean this propagation. How basically we do this by plumbing fixture and then we clear. So, but first, let's see why. I mean, this has the natural BB structure. So we can identify. So we had this general string field, which was a general element of this Hilbert space. So it has a Gauss number with all possible values from -infinity to +infinity. So what we decompose this in 2 ways. So the fields are identified with this particular combination, which is world sheet basis states they have Gauss number less than equal to 2, which means this target space field will have the Gauss number positive, greater than equal to 0. So all those combinations we call fields because they have this target space Gauss number positive, and anti-fields will have all the target space fields which have Gauss number negative.
So which one has positive was C or B?
I think C has positive.
C. So the vertex operators that you often said calling fields are those which are made mainly out of B's.
Not just. I mean, okay. So you could have said 3C and 2B. So
no, I mean more B's than C's.
Yeah.
Okay. The anti-fields are more C's.
Anti-field, yes.
Because yes.
I think maybe it's opposite.
Yeah, that's what
Yeah. So this world sheet Gauss number is in this capital G, and which means if it is greater than equal to 3, which means more C.
More C. So anti-fields are more C.
More C.
Should we have expected the other?
No, but somehow, yeah, here it is. So I mean, it is not that. For example, if you have this CC bar, that is part of fields.
Because equal.
Yes.
So the physical fields are part of fields.
So these physical fields, so all these target space fields psi s, which are greater than, whose Gauss number is greater than or equal to 0, they will be called fields of this BB. Whereas all these psi s, which have target space Gauss number less than 0, they will be called anti-fields of BB. And that, I mean, these anti-fields we denote, okay, we just put any star here, I mean, just to match notation with BB. So, for example, if you have this Gauss number, world sheet Gauss number 2, then target space Gauss number will be 0. These are classical space-time. And then if you have this world sheet Gauss number less than 2, then the target space Gauss number will be positive, and they are Gauss for Gauss, and so on. And then similarly, you have these anti-fields if your target space Gauss is negative. So this was the quantum master action. But now you can also write down the classical master action. So classical master action of the theory will be given by the same expression, but now you restrict the elementary region to only genus 0 contribution. So that will give you the this classical master action. And this action in particular has gauge invariance, and gauge invariance is given by this like transformation.
So quantum was that thing integrated over all
all genes. And classically,
factors of GA.
yes, that will have some factor of GS. And here it is like just genus zero.
Yeah, for genus zero, there are like things which is 1 and 2 functions.
Yeah, so for genus 0, 1, and 2 puncture will be in fact that n equal to 1 and 2 will be 0 actually for this. It should really start from n equal to 3.
Just out of curiosity, does the field redefinition work genus per genus? Just the classical.
Which so you mean the string field redefinition?
Yeah.
No, that will, I mean, so it depends on whether you are working with the full quantum theory or classical theory. I mean,
But if I just take the classical action,
yeah, that
then it
will be,
also
of course.
it will be field redefinition. And then okay, nice. So it's like more or less like a normal field.
Yeah. Yes. So
And then you will okay, go on. Then you will show us somehow this quantum action will include the divergences coming out of quantizing this classically.
I will not discuss the divergences, but I mean divergence. Which one? IR.
No, I meant the UV. Like
UV, there is no UV there.
yeah. So sorry. So good. Last time you had explained the difference. I thought you had explained that the difference between the quantum BB.
Yeah. So that
And
was in
classical
quantum.
UV.
I mean that was in quantum field theory.
Yeah.
But when you had UV divergences, here there is, even though there is no UV divergences, there is a correction coming from these hard genus surfaces. So they will be part of like so. Basically, I mean, this BB keep track of what is happening at the quantum level. This quantum master action.
There are new vertices and
New
every
vertices.
order.
Yes. Yes.
So it's not like you can take this classical action,
Yeah.
quantize it, and get all straight.
I mean, yeah. I mean, there will be. We'll have to keep track of these.
There are actually explicitly G-dependent
Yeah. So-
interaction vertices.
So that is one difference from like usual like quantum field theory.
Okay, then this I see. So it's not because the decomposition of the moduli space involves elementary blocks, right?
Elementary block.
But it's not as if in the full quantum theory your vertices are obtained through the.
Right. No, not just by this grouping, because there will be new vertices.
New vertex at the
from
top.
hard genus.
A new vertex at genus 2.
Yes.
A new vertex at genus 3.
Yes.
Because there's an elementary region in genus,
Yes,
genus 1 and an elementary region in genus 2.
Yes.
All these are treated as vertices.
Vertices.
And they can't be obtained by loops
Yes.
out of the
Yeah,
classical.
exactly, precisely.
So it's very uncertain. It's not a very nice definition.
But okay, I mean,
No, I mean it's fine to have a classical action with terms of order. Actions like that you explained. But to have an action that has all order coupling constant.
no, but so I mean, so you can have an analog of this classical action kind of S naught, where you include just the psi classical, which have only the physical fields, which worksheet.
No, that's
number
great. But
two.
you're saying that quantizing this
But-
will give you the right answer.
Because it says so that is a genuinely stringy feature. That's the like it won't. You will have to add something extra at like Haji.
Yeah.
So at the quantum level. So that's the difference from the usual like quantum field.
See, but just to understand that, because you can think of, say, torus diagram with vertices and
Yes.
so on.
Yeah.
I mean, as being built up by a more elementary building blocks, right?
No, so those will be like part of your this plumbing fixture which you get by this gluing this lower genus surfaces by
there will be
propagating.
more
But then there will
leftover
be leftover
which you won't get
which we
entirely
won't
from
get.
here.
Yes. So that's the like genuinely like.
It's another feature.
It's I mean it's an inconvenient feature. I mean we don't know. I mean how to deal with it, but yes, it is there.
Basically, this feature came because we moved up the modular space into different features.
Yeah.
Yeah.
And I would be happy if you did that on the sphere. And then quantizing that produce.
You get everything.
Yes,
Yeah, that should be very nice. Yeah. Then you could just take a work with this classical action and okay, you are done.
Yeah.
But it is like you have to like there is extra complication.
Okay.
This is much. If you do some field redefinition in the classical action here,
Yeah.
does it enter your kinetic term?
Field redefinition. Yeah, I mean, okay, so you can do field redefinition.
So from the interaction term, can it enter the
Interaction term. I mean, also you will do field redefinition of psi.
Yes.
So of course it will affect everything.
But the part which is affecting the interaction term, can it be
So, I
written
mean,
as Q psi?
Psi Q psi. So I mean, when you like do a field redefinition, I mean you are doing field redefinition not of interaction term but of psi, right?
Yes. And that will change your interaction.
Interaction term.
And
So it depends. Like what you can show is your S matrix will be independent of those field redefinition. Okay.
I think the question is if it affects the propagation.
So you can define a new propagator.
Yeah, that was the question. Like, will the propagator change if you?
Yeah, but this propagator will change in such a way that your S matrix remains in. So of course it will affect the propagator of I mean, if you do a field redefinition.
Uh, in
Yes.
in that master action,
Mhm.
it looks like if there are more size in the interaction, that term will be more suppressed. Is there a reason why that is the case?
More psi in the interaction term.
Yeah, if there are more size, that particular term is suppressed because
Yeah,
there is a one.
yeah, it depends because we are doing a perturbation theory. So you expect that hard genus, if for perturbation theory to make sense, these loop corrections. So it depends on like to what order in GS you want to work. So it will be suppressed in the usual way. I don't know if that answers the question, but
Okay.
He was talking about one.
oh, 1 by n factor.
But there's also this volume of integration, right? It's not so clear.
Okay.
But I mean, do the usual perturbation theory, then okay. I mean, this higher point, like in vertices, will be suppressed in the same way as you do, like this GS suppression.
Okay.
Okay, so the entry bracket of the theory now can be defined in the usual way. So you have this entry bracket f of g. So you have this derivative with respect to fields and anti-fields, psi and psi star, and then you also have this delta operator, and then you can show that the quantum master action satisfies precisely this BB quantum master equation. And on the other hand, the classical master action S, which you obtain by restricting only to genus zero contribution, that satisfies this classical master equation. And to prove both of these identity, you have to use this main identity. We had, and finally, you can also using this 1 pi vertices, you can also write down an 1 pi effective action, where now this you replace this elementary.
Sorry, but at some point you have this definition which which we talked a lot about defining a state from these psi stars.
This one.
No, before that, I think we talked a lot. Yeah, that this curly bracket then defined also some state.
Right. Yeah. I mean that appears.
Okay, I was going to ask you where that.
Yeah, that is in the equation. Yes. So here you can write down this, use this 1 pi effective vertices and write down 1 pi effective action. So the form is same, but what like vertex you use that changes the notion. And this 1 pi effective action satisfies the classical master equation because we are supposed to consider only tree diagram using this 1 pi effective action. And having constructed the vertices, you can write down an action and give a Feynman diagram interpretation to that.
Sorry, I was facing on you. How did you do this? S1pi was defined how?
So you have the same expression, but instead of this elementary vertices, you use this 1 pi.
Elementary was what?
So elementary was you obtained by integrating only over the elementary region.
Elementary
which had no denominations, separating as well as non-separating.
Okay.
And this 1 pi had elementary region as well as this non-separating type region.
No, it had non-separating.
Non-separating.
They have a next quick page, but they only have this guy.
Yeah.
But in S1 pi, we are considering only genus equal to 0 contribute.
Oh no, all.
I see. So basically, if you then.
Yeah.
This is what we would get if we, if the classical action just include the sphere functions and do the like.
No, that you won't get because you won't get this non-separating type.
One PI has that non-separating thing.
Yeah, one PI has non-separating type. So okay, so yes, so if you have a sphere with puncture, but then you not just glue two different sphere, but also the punctures on the same sphere. Yes, then you will get it. That's right. So with these vertices, suppose you want to compute the 4-point amplitude. So the 4-point amplitude will be represented in the usual way, like we represent Feynman diagram. So there will be a contribution which comes from this elementary like vertex with 4 puncture. This has no degeneration, and then there are 3 channels which are like obtained by gluing a sphere with 3 punctures by a propagator. So what is the like? How do we construct like these Feynman diagrams? So the Feynman diagrams are constructed by these what is called this plumbing fixture. So what you do is take 2 Riemann surfaces, say with genus G1 and N1 punctures and genus G2 and N2 punctures with some choice of local coordinates Wi around the puncture. And we glue these surfaces. So what you do is you cut a disc around some chosen puncture on these surfaces. And then you identify the local coordinates around these punctures in this way. So you have this, say, Wi1 represents on the first surface the ith puncture and coordinate around ith puncture, and this Wj2 represents the coordinate around jth puncture of the second Riemann surface. Then you just identify them in this way, where Q is some complex number parameterized by this S and theta.
Sorry, what are these dotted circle and dotted line represent? Not this one, the other one.
Oh, yeah. I mean, okay. These are some discs, and then these are some genus like holes and so on. Yeah, I mean, okay. For this like particular slide, all these have no term. I mean,
Yeah.
Not relevant.
Just a word about why is this a kind of natural thing to do? Isn't that maybe S goes to infinity or something?
Yes, yes. So there will be ambiguity, of course.
But this way of identifying is sort of natural or useful.
Yeah, I mean, this is what gives this like all this Feynman diagram interpretation.
Yes, some problem.
Right.
If I'm computing like an exchange diagram, then the external legs are automatically shaped of in theory. So you just have this surface with
This,
surface
right.
and the propagator.
Right. Yes. Right.
So you integrate over S.
We integrate. And that's where this ambiguity like comes. So for example, this.
Let's see. When you
Yeah, because that will be part of the moduli of this joint surface. This Q will be
so
like
it becomes like the proper time.
yeah. So this plumbing fixture introduces this. So this is the expression of propagator you have. So you have C0 minus, B0 plus, L0 plus inverse. But okay, I have skipped a lot of steps, and usually, I mean, there is an ambiguity in defining this, which comes precisely from this S. You can choose S equal to 0, say, or you can choose some S equal to S naught, and
How much of it
you are putting, and and then once you have this propagator, then say you want the S channel contribution, then in terms of propagator, it would be given by this. So you have this propagator in the middle, and then you have a sphere with 3 punctures, A1, A2, and so one puncture you like strip off and insert this complete set of basis state, which glues with this propagator, and then similarly on second surface, you have 3 punctures, but then you puncture one puncture you strip off, insert a complete set of basis states, and then this is the way you reproduce this S channel contribution to the.
I'm a bit confused. Do you integrate over S or is it you just keep it fixed because it's one choice of coordinates?
I mean, no, we integrate over it because it's part of the moduli. Moduli of
The
this
resulting
this.
Okay, so yeah, first there's a decomposition.
Yes.
Okay.
So-
The information about the S channel in this.
Oh, I mean S channel meaning I mean you have this K1, K2 separated and then K3, K4 separated. Like
And the basis
I think
is you can do similar thing if you have given A3
Oh, that will be some different channel. This is this channel.
But the thing that you insert in the middle will be same.
That will be the propagator. Okay, so this was the very sketchy introduction to this bosonic string field theory. But now we can generalize this construction to superstring field theory. I will just highlight the important differences.
You should keep it.
I will now very quickly finish. So the worldsheet theory of this closed superstring theory consists of now this matter field x mu and psi, and in the host sector you have BC as well as this beta gamma. And again, we consider the state space of worldsheet theory and restrict two states and highlighted by L0 minus and B0 minus. But unlike bosonic theory, we now have four different sectors: NSNS, NSR, RNS, and RN. And due to the bosonic host, we also have another quantum number in the system, which is this picture number. And the vacua of the theory will be labeled by these picture numbers. But there are an infinite number of vacuum now, which differ in picture number, but not all of these vacua will be useful. So the spectrum of L0 operator, you can show that it is bounded from below only for picture number -1 in the NS sector and picture number -half and -3/2 in the R sector. So in other picture number, the vacua fails to be annihilated by one or more of this beta n or gamma n with positive value of n. And by repeatedly acting with them on the vacuum, you can get states with arbitrarily large negative L0. Yes.
I thought there were four backwards.
No, that was bosonic theory. Bosonic theory. Here there is a picture number, so vacua will be labeled by picture number as well. So we shall make use of these picture number, namely -1 and this -half, -3/2 for constructing closed.
Very quickly, bosonic string. Like Raja's point, wait, the fact that there were four, did that mean anything?
No, I mean we are restrict. So ultimately we are just working with the two.
Which two?
I mean the one which are highlighted by this B0 minus, C0 minus.
B0 minus.
B0 minus and L0 minus.
And the fact that these two were both there, that played a role?
Yes. Because I mean
one of them was a field, the other an anti-field.
Yeah, I mean you will need them for the.
I see. In string worldsheet theory, we just use one of them.
Yeah, in string worldsheet, I mean they don't play a role because only the ghost number 2 are
I mean we just say B0 and
yes.
vertex operator 0.
That's it.
But here you actually keep
we
the other one.
We need this because to identify these anti-fields and so on.
And here there are no conditions on beta and gamma, like beta, like you had for B0 minus,
yes.
right? There are no such conditions for beta gamma.
I mean they will have some analogous property on the vacuum, so they will annihilate and so on.
But those will not be
yeah. So there no. So if you're asking condition like B0 minus equal to 0, no. So that we are not.
That is not.
Only condition we are imposing is that we work with this picture number. So they will have precise number of these modes. So now we can consider these two subspaces of this restricted Hilbert space, with picture number -1 and then -half, -3/2. So HC will now be this all state. So these represent all your four sectors. So H -1 means states with NSNS, and then this is RNS, but R with picture number -half and so on. So you have all these four sectors with picture number -half denoted by HC, and then you have H tilde C with picture number in R sector -3. So this is the way you decompose your Hilbert space. And BPZ inner product again. So now it will be non-zero only if the total picture number is -2, -2. It's a typo. So the total picture number in the two sector left and right should add up to -2. And this means the BPZ inner product will pair states with HC and H tilde C. So because if you have in NSNS you have -1, so they add up to -2. But in R sector, you need to add -half to -3/2 to get -2. That's why this BPZ inner product will pair states from HC with states from H tilde C. And the multilinear multilinear product again has the similar definition, but now this square bracket will belong to H tilde C, and these states A1 to A if they belong to HC. Now for writing down action, we need this another operator, which are the zero modes of this picture changing operator. So they change the picture number. So
The action of Q on this new square bracket will have same interpretation.
yes, so there will be okay, so there will be little modification due to this picture changing operators and so on. But yeah, it will have similar stuff. Well, same interpretation. So you have this G operator whose action on various components of Hilbert spaces H tilde C are given by this. So you have chi 0 when it acts on H minus 1 minus 3 half, chi bar 0 when it acts on H minus 3 half minus 1, and chi 0 bar for H minus 3 half minus 3 half. So the quantum master action is given now by this term. So here you have both in the kinetic term, both psi and psi tilde appear. Okay. So, and in the interaction term, only psi appears. So, since psi tilde only appears in the kinetic term,
Psi tilde was
psi tilde is an element of this H tilde hypothesis. And psi is an element of this HC hypothesis. Yes.
So a half a picture number, half integers are this R sector.
Yeah.
Corresponds to
I mean, minus 3 half also R sector.
And integer are the
NS sector. So psi tilde only appears in the kinetic term. So it describes a free field. But I mean, suppose you try to use only a single string field psi, then it will require an insertion of PCO. But then the inversion of kinetic term will not be well defined because the inversion of PCO inverse PCO operator is not a very well defined object. So that's why one has to introduce two kinds of string fields here, psi and psi tilde. And the equation of motion now takes this form. So if you vary with respect to psi tilde, you get this first equation, QB acting on psi minus G curly G psi tilde equal to 0. And if you vary with respect to psi, you have this equation. And you can combine these two equations to eliminate psi tilde, and you get equation of motion for psi.
Roughly speaking, you can integrate outside.
You can integrate out. Basically, yeah, you can, because it's just and again, you can give a BB interpretation. So again, you divide your basis states of HC and H tilde C in these states with positive and negative host number. And then you expand the string field. I'm very quickly going. So you can expand the string field in this way. And
one more time, show your action.
Yes. Yeah.
So once you integrated out the psi tilde, you still get the part of the result of integrating out psi tilde is also quadratic inside, right?
A result of you mean this?
No, just suppose I do a path. I integrate out psi tilde.
Okay.
Because it's
quadratic.
It was linear inside a coupling. So it was quadratic inside. So at the level of the action, we could just integrate out psi tilde.
Right.
And get.
Yeah, but I mean, it would be ugly, and I mean, it would not be a well-defined object.
Why not?
Because it will involve the inverse of this picture changing operator G. And that inverse of this operator is not a very well-defined. Because this G appears in the
Because you're saying that there was because G has some zeros?
G will have some zeros. In fact, people, before Ashok constructed this, people had tried to construct for R sector by inserting this inverse picture changing operator. But that was not a very well defined object.
I'm trying to ask if there was a problem before, why isn't there, if there are zeros, why don't we get infinity by integrating over the regions that are zero?
Now, okay, so now you can show that if you now the inverse of this operator is well defined. I mean, okay, I'm not deriving it, but it is well defined.
Inverse of Q.
These two terms. Inverse. So the kinetic term is both of these terms, and the inverse of this whole operator is now well defined. You can show that it will not involve the inverse of this curve. So that was the reason, in fact, and in fact, this is related to the fact that it's very difficult to write down action for the RR form fields, for example, pi form field, for example. So that is precisely connected with this. And once you have this kind of action, you can adopt it for writing down an action for this RR. Yes, I mean, Ashok has written down.
But I have that. Yes. Suppose QG has some zeros.
Yeah, but you also have to take into account this.
But it's quadratic thing. So we get determinant of QG.
Determinant of
When we do the path integral, that is linear times source. So that is just completing the square.
Yeah.
But we get determinant of QG. So maybe you're saying that maybe your point is that where there is a zero, there is no source.
Mhm.
Is that the point?
Yeah, I mean, okay, I've not thought from this point of view, but probably that is.
If I just drop the interactions, then at the quadratic level, you have the off-diagonal terms, right? So
Yeah,
would it be that the determinant with the off-diagonal terms is still?
Yeah, it's in fact, I mean, yeah, if you try to work out, if you try to write it down in a matrix form, you will see that the inversion does not have this gene. So it is written in terms of.
But I could try to do it in 2 steps. I could first just integrate out Q tilde.
Okay,
Now,
that will, I think probably.
I think what you want to say is that the source doesn't couple to the 0 points.
Right. So probably, yeah, in that language.
Because if that source coupled to the 0 point, we'd have a problem.
Yes. True.
So basically, this is well defined because where there is a 0 eigenspace, there is no source. From that point of view.
So source for cycle, right?
Yeah, that source is Q psi.
Q psi.
So Q psi will be a kind of source that will never couple to the 0 modes, and so on.
You were calling Q size source, I thought.
Yeah, exactly. Just I wanted to do 2 steps because cycle has like no role. Right? It's like Brazilian field. So might as well integrate.
But I mean, this play a role in open closed string.
Okay.
But okay. Let's see if you can reach there. So okay, so you can again give this BB interpretation and again identify the target space fields with positive host number as fields and target space fields with a negative host number as anti fields. You have this anti bracket which now get contribution from both sides I tilde and this classical master action again you can define by restricting to only inner 0 surfaces. And this classical master action has this kind of gauge invariance where you change both psi and psi tilde.
So fields and anti-fields are still whether more B's than C's.
Yeah, the same.
Same. And in both psi and psi.
Both sides. Okay, so and the classical action of the theory, you can again define a notion of classical action by restricting only to string field with host number, target space host number 0. Or basis space host number 2. And the 1PI effective action, again, you can give a similar interpretation. You can write down in terms of this 1PI vortices. And again, using this main identity, you can show that, okay, 1PI effective action satisfies this classical BB master equation. Okay, so that was this very quick, this type 2. And okay, I will very quickly say what is different in open closed. So in open closed, you have both closed Hilbert space and open Hilbert space. So again, in the open sector also, you consider these 2 picture number, -half, -3/2, and you have, you divide your Hilbert open sector in this way, HO and H tilde O. And this now string vortices, so now you consider this arbitrary genus surface will be described by some genus, then some boundaries, and with some open insertions and some closed insertions. And then you define elementary region in some suitable way. And this P form should have this dimension 6G - 6 plus 3B plus 2N plus M. And again, you can define these structures, these brackets in the usual way. But now all these brackets and all these P form, they have both open string as well as closed string. Again, you have this operator G, which have both, which when acting on open sector, they are defined in this way, and on closed sector, they are defined in this way. And the master action now is given by this. So the first 2 terms, they are the same as before. Okay, I'm changing convention. I'm putting GS in this also. It's just a different convention. Because I just took my slides from different sources. So, the first 2 terms denote the closed string kinetic term. This middle 2 term denote the open string kinetic term. The last term is the interaction term, and this one term is the 1-point function on the disk. This is 1-point function, 1-point closed string on the disk, so this you have to include separately because of this picture number like conservation, and because this is non-zero, this square bracket with no insertion, this you can relate it with some boundary state. Again, the psi tilde O and psi tilde C, they disappear from the physical processes. But now this psi tilde C, so this 1 point function on the like disk, so that that belongs to this H tilde Hilbert space, not HC Hilbert space, and the reason is so in the like so this D branes, so you D brane in the system, and these D branes carry RR charges, and these RR charges. So basically, this your D brane coupled to the this RR potentials, and RR potentials have picture number -3 not minus half. This -half picture number carry, I mean, they contain the field strength. So that's why this 1 point function, that this which is on the like which represents this closed string insertion on the disk, that belongs to this tilde Hilbert space. So that is why, I mean, this tilde is playing a role here. And then okay.
So when you are writing this correlator, you are working offshell, right? But these decouple on when you are when you write equations of motion. So on shell. So in any correlator, these will play a part, right?
In any correlator, I mean the interaction terms. You mean if you are like here, it will play, not in the closed string.
Yeah, here it will play, but here you have written that they again.
Yeah, I mean, provided you are not considering this kind of like processes, this D brane with this closed string insertion.
Like open closed kind of.
Right. Yeah, I mean, all these processes will be relevant for open closed kind.
Okay.
So you have this equation of motion, and again, by combining two, you can write down the equation for this psi C and psi O. And again, you can give a natural BB interpretation by decomposing in a like the suitable way. And you can expand the string field in this way. And again, you can consistently assign positive host number with the fields and negative host number with empty fields. And the gauge transformation of the theory will now involve all these fields. Okay, I will stop here. Yeah, I'm very sorry because I did not go too detail into this like geometric part, because that requires another set of like 3 lectures to really
Which geometric part?
I mean, all this PGN and so on. I mean, how exactly they contain information on moduli and those things. I did not really like discuss it. It was very superficial discussions.
I thought the lectures were fantastic.
Thanks, but
Is there an offer to give us 3 more lectures?
Could I ask?
Yeah.
Okay. So yesterday, when you started speaking formalism, you said that you start with an action. In the action, there are some fundamental fields. For each fundamental field, you will use a set of ghosts and anti-ghosts.
Right.
Here we did not see to do that.
Yeah, here, I mean, it was already present in the like, so string theory already has the BB structure. I mean, that is the beauty of a string theory. I mean, we don't have to like, okay, do something, I mean, by hand. I mean, okay, all that structure is already present. Inherently, I mean, it knows about BB and so on.
In the action itself. Yes.
I mean, in the like formalism itself, I mean, all this.
The string worksheet have hosts.
Yeah.
And those get promoted to hosts.
Yeah.
So, the space time host number, what is that?
Yeah, so that's something you assign. So so you have target space host number. Then you assign based on we have this definition 2 minus this worldsheet host number. We were calling the target space host number. And why that is a useful quantity? Because if you consider some S matrix, it will conserve that target space host number. So there is a simple analysis you can do. So that's why it's a consistent thing to like assign that target space host number.
I think I'm asking the same question in a different way, but what is the gauge symmetry? Is there like a gauge
Gauge symmetry?
Is there a target space gauge symmetry?
Yes, of course. So those will be, I mean, you can like work it out from like these expressions.
At leading order, it will be psi goes to q psi.
Yeah, leading order.
No, okay.
Leading order and because the action was psi q psi. So that will be left invariant by psi into q square because q is.
But is it like, does it have these spin free gauge transformations or not?
It's like different.
I mean, for metric, it will be different.
It will be infinite, right? It just q has all.
Yeah.
So that means
So you will get the usual thing from this Q.
All higher,
All.
higher massive pairs. It's a gauge transformation labeled by a string field. Every vertex of it. Just q psi is identity.
is it the same gauge transformation with the tensor limit?
Same gauge transform. So there will be some limit. I mean, okay, you have to work it out and what it will be.
What was the question?
Is it the same gauge transformations as the tensionless limit? Or is
So you have to take a suitable limit of okay this gauge transformation. There will be some alpha prime GS in this.
Sorry, one very big question. The thing that was really nice about well-sheet string theory was that it was so beautiful. And you just do integrals over Riemann spaces,
Yes,
you get
but I mean,
everything.
there was divergence. I mean,
No, so we can't live with that. But I was hoping that at the end of all of this, you will end up with something beautiful.
I mean, the point is, I mean, this has it still has the same structure. It's just that we are making it more well defined at the quantum level.
But okay, so the question is, suppose you do all of this,
Yeah.
then you get a rule for computing on-shell things.
So, right.
Now, can that rule for computing on-shell things be summarized after you've done everything
Okay.
in a simpler way than
yeah.
doing all this off-shell stuff?
Yeah, I mean, so for on-shell amplitude, what you can do, maybe computer can help you. I mean, there is this vertical integration procedures where they have some way of choosing a region in the moduli space, and that you can completely automatize and put it on a computer. But if you are asking some analytic way,
I'm not asking about that.
Yeah.
I'm saying you've got the rules for worksheet for computing
Yeah, I mean,
over Riemann circles
yeah.
were almost correct.
yeah, yeah.
So what are these divergences? They're not really, I mean, all the IR divergences are
It's
physical.
Yeah, they are there.
So
I don't.
For instance, if you try to compute the S matrix of a particle, and that particle has a renormalized mass.
oh, those kind of issues.
Yeah. So it's almost correct. What would be really nice is that if at the end of this you get some well-sheet, some Riemann surface prime, a small change in this that cures it, right? I mean, because that was so beautiful. Right now, what you're doing is taking the very beautiful structure, then breaking it up, making it very ugly somehow. And is that the hope?
Not, yeah, it's not very sure. I mean, it's
I mean, it's certainly correct.
Yeah.
I mean, no doubt. It sounds
Yeah.
fantastic
Yeah.
that you have the rules. It's very correct. But it would be sort of disappointing to me if this was the end.
yeah, yeah, it's very hard to say at this stage. I mean, whether we can give because right now the way it seems how you avoid this IR divergences, you have to do something like this. I mean, you decompose. Modelize.
At the end of your procedure, in the end, you've got some rule for computing on-shell amplitudes. Now, maybe that rule can be summarized in a way that doesn't require you to do all of
Okay,
this.
some on-shell way of. I mean, some. Okay.
I mean, wouldn't that be nice? Because I mean, one of the really beautiful things about string theory was that it was so elegant, right?
So maybe I mean this I epsilon prescription maybe can help at least as far as computing just amplitudes are concerned. Maybe if one could figure out exactly how this contour prescription works at all genus order, then this procedure of computing amplitude will reduce to that procedure. So it has been shown in the cases where it works. So maybe I mean if one works out that, maybe that is what you are hinting to.
I have one more question, but if you're getting late, we can talk at lunch.
Yeah, maybe let's go there.
Very nice. Very nice.